So in this lecture, I will discuss the orthonormal basis of a Hubble space. So the first theorem states that all Hilbert space contains an orthonormal basis. So there is at least one in each Hilbert space. And the proof is based on the zone lemma. So we have here X, a Hilbert space. And now we will define a new set, which I will call omega. And omega, it's formed by the elements of omega are orthonormal sets. So these are x theta, theta in I, and these are orthonormal sets. And I will introduce a partial order in omega. So if I have A and B, two elements of omega, which are, this means that A and B are orthonormal sets, I would say that A is smaller than B if A is contained in B. So if A it's a set of orthonormal vectors of X, well, A will be smaller than B if all these elements of A are also elements of B. So that defines clearly a partial order. So this is a partial order. And now let's check that the conditions of Zorn's lemma are fulfilled. So let's say that lambda is a subset of omega, which is totally ordered. So lambda is a subset, so the elements of lambda are families of orthonormal sets. So let's say that we have two elements in, so the elements of lambda, I call them AB. So lambda is family A, some sets, let me call that B, for B in some set J. And I'm assuming that lambda is totally ordered, which means that if I take A and B, two elements in lambda, either A it's contained in B or B it's contained in A. And now what I claim is that there exists an upper bound for lambda. So I claim that lambda admits an upper bound. And the upper bound, it's very simple. You just take A tilde to be the union over all elements of lambda. So I'm calling these elements AB, and I'm taking the union. So it's clear that A tilde is an upper bound for lambda. If you take any element of lambda, any element AB, AB is contained in the union, and therefore AB is smaller than A tilde for this partial order. So this means that we just proved that all totally ordered subset of omega has an upper bound, so that the assumption of Zorn lemma is satisfied, and therefore Zorn's lemma states that there exists a maximal element. So omega admits, has a maximal, there exists a maximal element in omega according to Zorn's lemma, which I already discussed in these lectures. So there exists a maximal element, so let me call x theta theta in some set I this maximal element. So let x theta be a maximal element. So it's an element of omega, which means that these vectors are all orthonormal. So it's a maximal element, and for that to be a basis, we need this set to be an orthonormal set. This is the case because omega is formed by orthonormal sets. But we need also the closed linear span of this set to be x. So we need to show that x is actually equal to the closed linear span of the x theta. And we'll proceed by contradiction. Well, assume it's not. Let me call this set y. So this set, it's a closed linear subset of x. So x, we know that it's equal to the orthogonal of y plus y. If y is different from x, it means that this set contains a non-trivial element. So there exists some y in y perp which is different from 0. Let me take z to be y divided by its norm. So z has norm equal to 1. And z belongs to y perp, which means that z is orthogonal to all elements of y, which means that z is also orthogonal to all x theta, which therefore, if I introduce z in this set, I get a new set, x theta, theta in I union z. This set, it's also an orthonormal set because, well, z has norm 1, x theta has norm 1. Inside here, they are all orthogonal because this set, it's an orthonormal set. And z, it's also orthogonal to all these sets. So this is a new orthonormal set. And it's strictly larger than this one. And this contradicts the fact that this set, it's a maximal element of omega, because we just found one element of omega which is strictly larger than this element. Therefore, if x is not the closed linear span of this set, this family is not a maximal element of omega, but we know that it's a maximal element of omega by Zorn's lemma. Therefore, we found a contradiction. And this completes the proof of this theorem. So now here is a useful lemma, which is called the Gram-Schmidt construction, or the Gram-Schmidt procedure or algorithm. So X is a Hilbert space. And I have here a family XP, P larger than 1. So this is a set which is either countable or finite. So it can be finite. And such that the XP are linearly independent. So I'm starting from that. I'm starting from a family which can be either finite or countable of linearly independent elements of X. And then what I claim is that there exists another family YP. And this one, it's an orthonormal set. So all elements of these sets have norm equal to 1, and they are orthogonal to each other. And this orthogonal set is such that, well, what I claim first is that for all m, the span of x1 to xm, it's equal to the span of y1 to ym. So what I'm claiming is that you can find a family, yp, such that for each m, the span of x1 up to xm, it's exactly equal to the span of ym, y1 to ym. And here I'm talking about linear span because, well, this is a finite set, so it's a linear span. And then second, I also claim that the cardinality of yp, it's equal to the cardinality of xp. So if this is a finite set which has m elements, this is a finite set which has m elements. If this is a countably infinite set, this one is also a countably infinite set. So I will prove this lemma now. The proof is by induction. So let me remember that we are starting from a family xp of linearly independent elements of x. So for p equal to 1, I will just define y1 as x1 divided by the norm of x1. So y1 has norm equal to 1. The span of y1 is equal to the span of x1. So up to now, everything is all right. So what I'm doing here, I'm constructing this family yp by induction. And I want that the linear span of y1 up to ym to be equal to the span of x1 up to xm. So I'm proving that by induction. I'm starting with p equal to 1. And now I assume that everything is proved up to p. So I know that the span of, or instead of p, let's say m. So I'm assuming that I already constructed y1 up to ym, that this family is orthonormal, and that the span of y1 up to ym is equal to the span of x1 up to xm. And now I have to construct ym plus 1. So ym plus 1 will be equal to xm plus 1. Let me put a hat because then after that I will have to normalize this vector. So let me define ym plus 1 hat as xm plus 1 minus, well, the sum from 1 up to m of xm, xj, xm plus 1. So I'm defining this new vector, ym plus 1, with from these y1 up to ym, which I already constructed, and with xm plus 1, which is given by this formula. Now I claim that ym plus 1 hat is orthogonal, to all the previous one. So this is the first thing I need to check, because I want this set to be formed by orthogonal vectors. Well, so in order to do that, let's take the scalar product of this vector with yj from this identity. So ym plus 1 yj this is equal to xm plus 1 yj minus, well, by linearity, I get that this is equal to the sum of j from 1 up to m, or let me put here the sum from k from 1 to m of xm plus 1 yj. So this is by linearity, this goes out. And then here I have yk, yj. But yk, yj, since they are orthogonal, this is either 0 or 1. 0 if k is equal to j, and 1 if 0 if k is different from j, and 1 if k is equal to j. So you see that in this sum, all terms vanish but the one in which k is equal to j, and therefore this sum, it's equal to xm plus 1 yj. So we have xm plus 1 yj minus xm plus 1 yj. So this is 0. So we proved that indeed this vector y hat m plus 1, it's orthogonal to all yj from j from 1 to m. So this is the first claim. Then my second claim is that these two spans are equal now if I replace m by m plus 1. So let's check that. Well, let's say that we take x in the span, linear span of x1 up to xn plus 1. This means that x can be written as the sum from j from 1 up to m plus 1 of alpha j xj. Alpha j are scalars, and to say that x is in the linear span means that x can be written as a linear combination of this xj. Now, in this sum, I have one term which is y alpha m plus 1 x m plus 1. And then I have a sum from 1 to m of alpha j xj. But the span, so what remains here belongs to the span of x1 up to xm. And by the induction assumption, this span, it's equal to the span of y1 up to ym. So this means that I can express this vector as a sum of beta j yj, because the spans coincide. On the other hand, I have here xm plus 1. xm plus 1 can be expressed in terms of the yj and y hat m plus 1, which means that this vector x can be expressed in terms of y1 up to ym and y hat m plus 1. So this proves that the span of x1 xm plus 1, it's contained in the span of y1 up to ym y hat m plus 1. And the same argument shows that the span of y1 ym y hat m plus 1, it's contained in the span of x1 xm plus 1. So actually, these two linear spans are equal, and this is getting closer to what we want to prove. We want to prove that the span of y1 up to ym plus 1 is equal to the span of x1 up to xm plus 1. But now, if I define ym as ym hat divided by the norm of y hat m, well, the span of y1 up to ym and y hat m plus 1, it's equal to the span of y1 up to ym plus 1. This is a simple exercise. So this identity, it's a simple exercise which I leave it to you to check. So from this identity, we get this identity. Also, here it's m plus 1, I'm sorry. Also, ym plus 1 has norm equal to 1. And ym plus 1, it's orthogonal to all yj because, well, it's a scalar times y hat m plus 1, and y hat m plus 1 is orthogonal to all yj. So indeed, this family up to m plus 1, it's an orthonormal family, and its span, it's equal to the span of x1, xm, and this was my first claim. So we started from a family xp, p larger family which is either finite or countable of linearly independent vectors. So now there are two cases. Assume that it's a finite family, so we have x1 up to xm. And in the, well, what we did up to now, it's that we constructed a family y1 up to ym, which is an orthonormal family, an orthonormal set, and the span of these two sets are equal, and this proves the lemma. Because, well, in the lemma, remember, we wanted to construct this family of orthonormal sets whose span is equal, and we also wanted to show that the cardinality is the same. Well, but by construction, we get the same cardinality. There is well, the second alternative is that we have here a countable family, and by induction, what we proved is that in this case we can construct a countable family of orthonormal sets such that if I fix M, the linear span of x1, xm, it's equal to the linear span of y1, ym. And again here, this set it's countable, we constructed a countable set, so both cardinality are equal, and that completes the proof of Gram-Schmidt lemma. So in what we just proved is that if we started from family which can be either finite or countably infinite of vectors which are linearly independent, then from this family we can construct a new family which is now orthogonal and whose vectors can be made to have norm equal to 1. And that can be very useful in order to construct orthonormal bases. Now I will prove a lemma which states that every basis has the same cardinality. So let's consider X, which is a Hilbert spaces, and let's assume that it has two different orthonormal bases. One which I'm representing by x theta, where theta belongs to some set I, and the other one y beta, in which beta belongs to some set J. And I'm assuming that those two are different orthonormal bases. And what I want to prove is that the cardinality of this set is equal to the cardinality of the other set, which means that, well, if this set is finite, then this set is also finite and they have the same number of elements, while if they are infinite, well, their cardinality are equal. I leave it to you as an exercise to prove this lemma in the case in which one of these sets is finite. You can use Gram-Schmidt in order to show that the number of elements are exactly the same in both sets. So let's assume here that one of these sets is infinite, and let's prove that they have the same cardinality. So in order to prove that, let me fix a theta in I. And for that theta in I will define a set, which depends on this theta, which is all betas in J, for which the scalar product of x theta, so this element with theta fixed, with y beta, it's different from 0. we know that this family is at most countable. So there are at most countably many betas for which this scalar product is different from 0. So this is one fact which I wrote here. J theta, for each theta, J theta, it's at most countable. And on the other hand, well, J theta, it's of course a subset of J because it's made of elements of J. Now, what I claim is that J, it's included in the union over all theta in I of J theta. So let's say that you have an element of J. So an element of J, let's say it's beta. Let's take a beta in J. Let's consider Y beta. Well, Y beta, since x theta it's a basis, Y beta can be written in terms of, well, it belongs, Y theta belongs to the closed linear span of x theta. So remember that if a set it's a basis, it means that its closed linear span it's equal to the entire space. So Y beta it's an element of X. So it belongs to the closed linear space. In the case of Hilbert spaces, we proved in the last lecture an explicit formula for the closed linear span. So we proved that Y beta can be written as a sum of Yk, k larger than 1, of x theta k. Since the norm of Y beta is 1, Y beta is different from 0, so there is at least one of these coefficients alpha k which is different from 0, and we know that alpha k it's equal to Y beta x theta k. So since Y beta is different from 0, there is at least one k for which alpha k is different from 0. Alpha k is equal to Y beta x theta k. So this is different from 0. And this means, therefore, that beta belongs to G theta k because, well, Y beta x theta k is different from 0. So beta belongs to G of theta k, which shows that, indeed, beta belongs to this union. And that proves this relation, that the set J it's included in the union over all theta in I of J theta. But, well, since this set here has it's countable, and since the countable sets are the infinite sets with the least cardinality, it follows from this inclusion that the cardinality of J it's smaller than the cardinality of I, right? Because J it's contained in union over I of countable sets. And since the countable sets are the infinite sets with the least cardinality, we get this inequality. And by inversing the roles of I and J, we can obtain the other inequality saying that the cardinality of I is bounded by the cardinality of J, from which it follows that the cardinality are equal. And it follows from this result that we can define the dimension of a Hilbert space. So the dimension, this lemma entitles us to introduce this definition. If I have a Hilbert space X, I'll say that the dimension of X it's equal to the cardinality of an orthonormal basis. This is well defined by the previous lemma. So let me complete this lecture, this short lecture, with a remark. We proved the Bessel inequality. So let me recall the Bessel inequality. It states the following: assume that you have x theta, theta in I, an orthonormal set. So I'm not assuming that it's a basis. I'm just saying that it's an orthonormal set. So now let me take X, an element of X. let me define alpha theta as x, the scalar product of x with x theta. We have seen that the family of thetas for which this is different from 0, it's countable. And what we proved is that alpha theta square, the sum, let's say, of theta in I, that this is bounded by x squared. So this is Bessel's inequality that, well, we proved first that this, the set for which this is different from 0, it's countable. So here we have at least, at most, a countable number of thetas for which this is different from 0. So this sum makes sense. We proved not only that this sum makes sense, but that it's the squares, the sum of the squares is bounded by x squared. So this was Bessel inequality. So let me rewrite it here, that since alpha theta it's x theta, let me write it in this way. X theta square, it's bounded by x square, in which theta runs in I. Now, what I want is to replace this assumption that x theta, theta in I, it's an orthonormal set by a stronger one. I will assume that this is an orthonormal basis. So now I'm assuming that actually the closed linear span of x theta, it's all x. And again, I fix x in x. So now, since this is a basis, and I used this fact before in this lecture, the closed linear span of this set, it's equal to x. But I know exactly what the closed linear span of this set is. This is the sum of alpha j, j larger than 1, x theta j, where here, well, the alpha j's are scalars. They are square summable. And theta j belongs to I. So this is, we proved that the closed linear span, it's given exactly by that set. And since x belongs to x, well, it can be written in this form. So x, it's equal to the sum of alpha j, x theta j. Now remember that this sum, this infinite sum, has to be understood as the limit of the finite sums. So I have two claims. The first one is that alpha j, it's equal to x theta j. Then the second is that x theta, it's equal to 0 if theta is different from theta k. So if theta doesn't belong to this set theta k. So this set which appears here in this sum. And finally, what I claim is that the norm of x squared, it's equal to the sum for j larger than 1 of alpha j, but alpha j, it's x theta j squared. And, well, and since x theta it's equal to 0 if theta doesn't belong to this set, I can rewrite that as an infinite sum over all theta in I of x theta square. And here you see that, well, again, this sum, it's actually at most countable because all terms are 0 but a countable number of them. And so this sum makes sense. And what I'm saying is that this sum, it's equal to x squared. And this is called Parseval identity. And my point here is that, well, Parseval gives you an identity because this family, it's a basis. Knowing only that the family, it's an orthonormal set, what you can show is that this sum, it's bounded by the norm square. But if it's a basis, all terms are there, and therefore you go from the inequality to an identity. So maybe let me state that as a lemma. The lemma reads as follows: take x theta, a family which is an orthonormal, and it's a basis of the Hilbert space X. So X, again, it's a Hilbert space. Now, what I claim is that, well, let me call alpha theta, if you wish. So my claim is that X in X, then X can be written as x theta, theta in I. And this is well defined again because, well, this vanishes for all but a countable number, at most a countable number of terms. And the second statement is that the norm of x squared, it's equal to the sum in theta in I of x theta squared. So this is what I just stated here in other terms. So let's prove that this lemma and again, this is what we called Parseval identity. So let's prove that. Well, since x belongs to x, and this is a basis, x it's equal to the closed linear span. The closed linear span is given by this expression. So there exist alpha j's and theta j's in I, alpha j's in k, such that x it's equal to alpha j x theta j. So let me call Zm this partial sum. And by definition, x is the limit of Zm. So we know that not only these alpha j's belong to k, but the sum of the squares, it's finite. So now I first claim that alpha j, it's equal to x theta j. And why is that? Well, because x theta j, because the scalar product is continuous and x is the limit of Zm, x theta j is the limit in M of Zm, but Zm it's the sum from 1 to M of alpha k x theta k. So x is the limit of Zm, therefore the scalar product, it's the limit of the scalar products. By linearity, this goes out. And since this family, it's orthonormal, these terms are all equal to 0, but the one in which k it's equal to, so this is sum in k, the one in which k it's equal to j. So for m larger than j, this scalar product, it's equal to alpha j, and therefore the limit, it's equal to alpha j. So this proves my first claim. So all these alpha j's are actually x, the scalar product of x with x theta j. My second claim is that if theta doesn't belong to the family theta j, then x theta it's equal to 0. So x it's orthogonal to x theta. And this comes from the same computation, x theta. Well, it's the limit in M of the sum for k from 1 up to M of alpha k x theta k, x theta. But since this is an orthonormal set, and theta is different from all theta k's, these scalar products are equal to 0. Therefore, all these terms are 0. Therefore, well, this is a constant sequence equal to 0, and it's limited 0. So we proved the second statement, which is that x it's orthogonal to all x theta. So let me write we proved that alpha j it's equal to xj. So this is x theta j, sorry. And we proved that x theta it's equal to 0 if theta doesn't belong to the family theta k. Now, let's finally prove this identity. So x squared it's equal, well, x is the limit of Zm, so the norm square is the limit of the norm square. But Zm is given by this sum. All these vectors are orthonormal, so they have norm equal to 1 and they are orthogonal to each other. So this is the limit of, so I leave it to you to compute the scalar product of Zm with Zm. What I claim is that this is equal to the sum from 1 to m of alpha j square. And the limit in m of this expression is the infinite sum. So this is equal to the sum for j larger than 1 of alpha j square, but alpha j it's x theta j. So this is equal to the sum in j of x theta j square. And now, since x theta is equal to 0 if theta doesn't belong to this set, I can add to this sum all terms, all the other terms, because they are all equal to 0. And from this, I get the third claim, which is that this identity, which is called the Parseval identity, holds. So let me just rephrase everything, that if x is a Hilbert space and we have a basis x theta, then any element x can be written as an infinite sum of the scalar product of x with x theta times x theta, because, well, all these scalar products are equal to 0, but at most a countable family. So this sum, it's actually a countable sum. And it makes sense because this sum of the sum of the squares, it's equal to the norm of x squared, which is finite. Therefore, this sum is finite, and we have seen that whenever this sum is finite, we can make sense of this sum as a limit of finite sums. So this proves the last lemma of this lecture.